So far in chapter 2, we've gone over sequences, arithmetic, geometric. We talked about how arithmetic and geometric sequences are related to linear and exponential functions. We really talked about linear functions in the first quarter, and now we're going to spend a bit of time talking about exponential functions. So the rest of this part of this unit, so unit 2, part 1, is going to be focused on exponential functions. So let's get some of the basic characteristics of exponential functions ironed out between us. Now, exponential functions themselves are some of the most important functions in the world. They appear in population growth, money, interest and debt, radioactive decay, carbon dating, the spread of disease, a lot of things like that. So we need to understand the different pieces of an exponential function so we understand its behavior. An exponential function has the general form a times b to the x. What's the general form? A times b to the x. One more time.
A times b to the x.
Great. Let's highlight the a in green and the b in blue. These two letters are going to represent very specific things when it comes to the exponential function. The a, which is green, represents what we call the initial amount. We would also potentially call this the y-intercept. So whatever number is in front of the base with the power is our y-intercept, or the initial amount. The b represents the base, or in sequences, it would be called the common ratio. Or sometimes it's referred to, especially in real-world scenarios, it's called the factor. So base, or common ratio, or factor. I'm going to mostly refer to it as the base, but it also has those other names. Now, depending on what sort of number you get for A and get for B determines the shape of the exponential curve. These curves go in one direction only. You either have an exponential growth. You get exponential growth when B is greater than 1. We see how it's growing. We get exponential decay when the B value of the base is between 0 and 1. That's blue. They're both blue on purpose. The B represents either growth or decay, whether my factor will be multiplying by a number that makes things bigger or makes things smaller.
So E, for instance, if it's 0.8?
Would be decay. 0.8 would be decay. The A value, since it is my initial value, it is the y-intercept. For both of the examples posted on your paper, that A value is positive. So you see how our graph is above the x-axis for both of these? That's because the A value is positive. If we make that A value negative, what it does is it reflects the graph over the x-axis, and we would just have exponential growth and decay, but in the bottom two quadrants instead of the top two quadrants. There's one more thing we're going to highlight here that's very important. Just like our rational functions, exponential functions have horizontal asymptotes. These are the lines that the graph is going to get very, very close to but never touch. For both types of functions, a non-vertically transformed graph is going to have a horizontal asymptote at y equal to 0. Which means that our graph is going to get very close to but never touch the x-axis, the line y equal to 0. There's some other key characteristics when it comes to the shape of exponential functions, which we need to get pretty good at understanding the general shape, growth, decay. If A is positive, it'll be above the x-axis. If A is negative, it will be below the x-axis. Some other key characteristics here that we will talk about with most functions we learn about. This function, an exponential function, is always increasing or always decreasing. It never switches. So in polynomials, when we learned about maximums and minimums, they were where we went from increasing to decreasing or decreasing to increasing. So since this never changes, whether it's increasing or decreasing, we're going to have no extrema values, no maxes or mins. Also, exponential functions are always either concave up or concave down. They'll never switch concavity, which means we also have no points of inflection for this graph. The end behavior of this graph is very interesting. If you notice in our pictures, on one side, the graph is going up, and on one side, what are we getting close to? Are we? We're going back up? It's like getting close to horizontal asymptote, yes? Which for us in this picture is what number? 0. So our end behavior is going to be one side going to 0 and one side going to infinity. So if we write that as a limit statement, which is our goal, one of our goals of today is to write these limit statements. If we have an exponential growth graph, which you notice has an A value that's positive and a B value that's bigger than 1 and a horizontal asymptote at 0, you're going to see this color scheme a lot today. We would say that as we go to the left side, our left side end behavior as x approaches negative infinity is going to get close to that horizontal asymptote of 0. But on the right side, it's going to extend up and up and up and up, which means on the right side, an exponential growth equation will be, the end behavior will be approaching infinity. For an exponential decay graph, again, for this one, my A value is positive. My B value would be between 0 and 1. And then we have a horizontal asymptote. The left side, as x approaches negative infinity, will be going up. The right side will be getting close to that horizontal asymptote of 0. So with polynomials, we had infinities as our answers. Is either both up, both down, one up, one down, or the vice versa. For exponentials, one side is going to flatten out at 0. So these shapes are a little bit different. Let's see if we can just write these limit statements first before we complicate it with some other characteristics. So if we're looking exactly at this picture, what I would like for us to do as we get used to these pictures is identify what kind of A value and B value we have always. Is your A value going to be bigger than 0 or less than 0?
Bigger.
Bigger than 0. What kind of B value will you have? Bigger than 1 or between 0 and 1? Bigger than 1. So this is B greater than 1. That's just good to keep in mind so we remember how the formula might look for this later on. But if we're looking at this graph, what is happening on the left side of the graph? What are we getting closer and closer to? The horizontal asymptote. So what is the equation of the horizontal asymptote here? What number is it at? 0. So we would write a limit statement. The limit as x approaches negative infinity for the name of this function being f, we just decided to name it that, would be equal to 0 because we're flattening out at the horizontal asymptote. What's happening on the right side of this graph? It's going up, so my limit is going to approach what? Infinity. This is the limit as x approaches positive infinity. That means go to the right side. Our end behavior is infinity. Here's our first example where the A value has changed. Do you notice for graph B that the initial value is below the x-axis? Yikes. That means that the A value here is less than 0. This graph has been reflected over the x-axis. This is where it gets a little tricky to determine how B behaves. So is this graph, as we read it from the left to the right like a regular book, is it getting closer to the x-axis or further away from the x-axis? That means that things are getting smaller, which means that for this one, B is between 0 and 1. This is an exponential decay function that has been reflected over the x-axis. It's still decay. Either way, when we look at this graph and we adjust for the horizontal asymptote, which is still 0, if we write the end behavior on the left side, the left is as x approaches negative infinity, as it decreases without bound. What's happening on my graph on the left side here? Interesting, right? What's happening on the left side here?
It's not at 0.
It's not at 0. What is it going towards? Negative infinity, because it's going downwards. Interesting. So if our a value is negative, we're approaching one of the negative infinity. But let's see what's happening on the right side. What's happening on the right side of this graph? It's getting closer to 0. So the outputs approach 0. We say as x increases without bound for f of x, the outputs approach 0.
So the opposite one is
Below.
yeah.
It depends on both A and B. So don't just automatically think if A is negative that it's this the answer. We do need both the A and the B shape to give us this answer. So the reason I've been having you write about A and B this whole time is because I'm not always going to give you a picture of what the function will look like. And I know you have your calculators today because we just took the quiz with the calculators. But a lot of these questions come on the non-calculator portion of your test. So we need to be able to visualize what this shape looks like just from the equation itself. Looking at this equation, what is the A value? 5. Is that greater than 0 or less than 0? Greater than 0. Okay, what's the B value?
230.
Is that between 0 and 1 or bigger than 1?
Between 0.
So we should know, based on this, that our graph might look something like this. We have a y-intercept that is above the x-axis, and we have a decay shape. We know this from the initial value and the base.
Would you like us to draw the graph for everyone?
I would, not just for me, but for you. It will make a lot more sense answering the questions I'm going to ask you about the shapes if you've drawn a picture every time. So anytime you get an exponential function, draw yourself a little sketch so you know what it looks like. If we talk about this one, for the end behavior, the limit as x decreases without bound, so as we go to the left, what is happening? On the left, what's happening?
Oh, it's getting close to positive infinity.
It's approaching positive infinity. Did you notice I switched letters on you?
Yeah.
Why did I switch letters?
G of x, because that's what the function says.
Yeah, because it's printed on the paper that way, yeah. If the function is named g, call it g. What's happening on the right side for the limit?
It's reaching 0.
It's approaching 0. Very good. Okay, so the limit as x approaches infinity of g of x is 0, because we're getting closer to that horizontal asymptote. Questions, comments, concerns about end behavior? Here's what I care about. Before you flip this over, I want you to look at your neighbor's paper. Did they stack their limit statement? Is the limit above x approaching the infinity? The reason I'm being annoying about this is because I know in Algebra 2 when you wrote limit statements, you wrote them flat. That's not acceptable in this class. You have to stack them, limit above x. We're using calculus notation since this is a pre-calculus class. You have to stack them. I'm going to count it wrong if you write it incorrectly. I know we've practiced this before, but I want to be perfectly clear about that.
You see if you stack it down.
No, but if you wrote it flat.
All right, on the back, we're going to continue talking about the characteristics of these functions. Not necessarily their end behavior anymore, but their characteristics. I want to stick with this color scheme we've been using and writing down the A's and the B's because it's good practice. So for question A right here, before we even read anything, is the A value positive or negative? Positive, because it's above the x-axis. So we know A is greater than 0. Would this be growth or decay?
Growth.
For real?
Oh, no.
I didn't even look at it. Yeah, this would be decay. I just want us to practice this so we always know how to draw the shape. This question in particular, though, asks us to determine if the exponential function is increasing or decreasing and whether it's concave up or concave down. Decreasing, because what's happening? It's getting closer to 0, but also if you were walking on this, you'd be walking downhill. That's decreasing. So we know that this one is a decreasing function. Let's talk about concavity. Remember, concave up is when you have your wrists together, fingers pointing to the sky. Concave down is fingers together, wrists toward the ground. Is this concave up or concave down? Nice, concave up. Bonus question here. What is the equation of the horizontal asymptote?
Oh, can I do it?
Yeah.
Why you not write it first and then tell me?
Well, Ian just said it. What is it, Ian? Y equals 0. Very nice. Let's go to the letter B. Okay. Again, before we answer the actual question here, let's identify A and B. Is the A value above 0 or below 0? Below. So this is A less than 0. This is a tough one, so don't say anything out loud. Think for a second. Is this going to be growth or decay?
It's decay, right?
No, it's growth.
This is growth.
Yeah.
This is growth that has been reflected.
Hold on, why is it growth?
That's
It's still going, it's like going X, so like it's still going to the
You're
right.
gonna have to go.
Oh, it's going down, but it's going to the right.
So this is growth, yes?
Yes.
If I take growth and I flip it over the x-axis, this is what it would look like. This is a reflected growth graph.
You're gonna have to
So
go
will we,
back to
like-
geometry for that.
How do I put this? We would like reflect it and like we would go based off of that, like.
Yeah, so A and B are numbers. If A is negative, it's a
So
reflection.
would this be increasing?
That's a great question. If we were walking on this graph, would we be walking uphill or downhill? This is still a decreasing graph. This is why it's confusing.
Okay, concave down and decreasing.
But it is concave down, yes. So don't automatically think growth means increasing. It could be a reflected growth graph where it is a decreasing function. Confusing, I know.
It's growing, but it's decreasing.
I know. That still don't make very sense.
Okay, I've been making you write the A's and the B's this whole time so that, again, we can adjust for the shape of a function. In this letter C, what is the initial value? 3, which means is this graph going to be above or below the x-axis? Above, nice. And then is this base, oh, what is the base? 4, so is this growth or decay? Growth. So we should have a growth function that looks something like this. Let's describe this one. Is this increasing or decreasing? Increasing. Concave up or concave down? Concave up. So that we can mix and match these pieces of information. The main idea here, though, is that if we can just sketch the shape, we're going to be able to answer a lot of questions about the function itself. For example, and I'm skipping something on purpose, go to example 4.
Where?
Just scroll down. It says the function f is given by f of x equal to 5 times 0.7 to the x. Which of the following describes f? Before we do anything and read any answer choices, what does the shape of this function look like?
Would it be, would it start?
I think it would be decay.
Well, here's my question. What's the initial value?
5.
So is it above or below the x-axis?
It's above, but it'll eventually go down.
Agreed, because we have a decay factor there. So we're going to have an above but decay graph. It's important to know the shape because now we can answer this question really well. You guys are right. What kind of exponential function is this? Growth or decay? Decay. So get rid of C and D. They're gone. Those say growth, which is wrong. Now we need to know what's happening. It's getting closer to 0 as we go to the right side. So if we read these limit statements, it says as x goes to the right, what's happening? We see from our picture that we're getting closer to 0. Giving me the shape of the function is very, very helpful.
Wait, miss, can you explain why example 2B is growth?
Yes, I can. Okay, we're going back up here. Remember, typically growth looks like this. Yes? What if I reflect that growth graph over the x-axis? If I reflect it, it's still growth, it has just been reflected. Because if you're walking on it, the outputs are going down, so it's decreasing. So decreasing and increasing doesn't exactly mean growth and decay anymore. You have to actually think about the shape of the function. Are the outputs values increasing or are the output values decreasing? That's a good question. Okay, continuing on, let's go to number 5. Same vibe. We have a different equation here and we're still going to ask you to describe the function. I'm going to pause here and I want you to try this one. When you drew your exponential, did it look something like mine?
Yes.
Nice, because we have an initial value of 2 and a factor of 3 over 2, which is bigger than 1, so this should be growing. So which 2 answer choices can I get rid of? A and B here say exponential decay. Wrong. This time, if we're looking to the right, our limit is going up to infinity. Very cool.
Let's talk about example 6 now.
You're right. Let's talk about example 6. It says the value 2 times 2 times 2 times 2 times 2 times 4.7 is the output value of an exponential function a times b to the x. Which of the following describes the function and input value that corresponds to this output value? Now, this is rather annoying to write 2 times 2 times 2 times 2 times 2 times 4.7. Mathematicians got tired of writing 2 times 2 times 2 times 2 times 2. How else can I represent? To a power. 2 to the power of 5 is now going to be multiplied by 2.7. And if I just rewrite this so that it actually looks like an exponential, I could write it as 4.7 times 2 to the 5th power. So what's the initial value? Which means it's not A or B because they have the wrong initial value.
The input value is 5.
And what number had I plugged in here? 5. So let's just make it into the correct formula so we can talk about the characteristics of the graph. Now, of course, I skipped number 3 on purpose. We can't just leave it there. We are going to go back to it.
It's gonna be the easiest one on
You're sleeping a lot.
Wait a minute, go back.
Okay, thanks.
Okay, you're welcome. If I look at number 3, it asks me to take the selected values of the function f that are shown in the table and determine if f could be linear, quadratic, exponential, or none of these, and give an explanation of why. Let's see. First things first, we check the input values. How are my input values changing?
Plus 5.
Plus 5. So we would say they are equal length input value intervals. And I didn't leave a space for us to put the plus 5, so remember you're always wanting to give me all of the details, so you're going to sneak a plus 5 right there. That's how the equal length input value intervals are changing. Let's check the output values now. How do I go from 3 to 5?
Plus 2.
How about from 5 to 9?
Plus 4.
How about from 9 to 17?
8.
And then
You lost me. Wait, plus 6. No,
Wait.
16.
16.
Oh, wait. And then you would do those. You would do the,
Okay, stay with me. If these numbers were all the same, it would be linear. Are this first differences constant to make this a linear function? No. We try the second differences to see if it's quadratic.
That's times 2
times 2.
Oh, wait. Quadratic is still adding and subtracting. How do you go from 2 to 4 with adding and subtracting?
times 1.
Times 1 half.
Times 1 half.
Stay with me. Adding and subtracting.
Wait, why are we adding?
Quadratic is all about the differences. So you're still adding and subtracting the differences.
So which one was multiplication?
Where it's coming. So this one didn't work either.
Rate of change.
This is quadratic. What y'all are thinking of is what we did last class, where we went back to the original ones themselves.
That's what I was
That's what I was thinking.
What? Sorry, what?
We're using quadratic now?
We always were.
What? Wait. on the other one we weren't, you said we weren't, like neither was quadratic.
Yeah.
On the classwork we did last
the
class,
rate of
quadratic was an option, the change in the rate of change. Stay with me, stay with me. The linear differences did not work. So we try the second differences. Those are not the same. We go back to the original questions and we try multiplication. To go from 3 to 5, I'd have to do times 5/3. To go from 9 to 5 to 9, sorry, I have to do times 5/9. 9/5, wow. Here's my question. Are those numbers the same? No. Jasmine, you saw this from the beginning. Is there any particular pattern in these numbers?
Miss, why would you make it so complicated though?
Yeah, you could make it more complicated.
Miss, I was
You could have
like,
just
wait,
put
am I
that.
wrong?
Here's why I made it complicated. We now have to speak to why none of these worked.
I don't want to speak to
Yeah, but I don't want to do it.
Too bad, we're doing it. It says to explain why. This function f could be neither, because over our equal length input value intervals, the output values of x
Okay, let's say
do not change at a constant rate. If it changed at a constant rate, that would make it linear. So it's not linear. The output values do not have a rate of change that changes at a constant rate, which would make it quadratic, nor do they
have proportion.
They do not, there it is, they do not change proportionately, which would be exponential.
Is there a shortcut?
No.
I can't fit it all
Here's the thing. I know your handwriting is really big, so you're making a good point. Grab a post-it note and add on to it. In this class, it is important to be able to properly communicate the math that we are learning. This is proper communication. I don't want to hear it. This is proper communication. You do need to be able to write explanations for me. This is a writing class.
I do have a question though.
Okay, I'm listening now.
Okay, so let's say the EXP, I forgot what it's called.
Exponential.
Exponential, let's say it did change. So we'd say it doesn't have a change at a constant rate. It does not change at a rate of change, but then we would say it does change proportionally.
You would only have to say that they change proportionally.
Man, that's too much.
So if it's one of the three options, you just have to tell me why it's that option. If you're trying to prove to me that it's none of them, you have to disprove all of them.
That's not.
Clearly communicating what you're trying to answer is very important.
I don't feel like we're gonna write it.
Let me say that again because I think that made it clear. Wherever you're finding the change and the change is the same the whole time, either +2 the first times, +2 the second times, or like ×3, that's what function type it is. And you just have to explain to me why it's that function type. We didn't have any of those function types, so we had to disprove all three.